Check this morning.
Is this working?
Yeah, we can see the slides. Thanks.
Yeah, okay.
Mokshit? Hi, Mokshit. Would you like to be interrupted during your talk, or should we rather wait until the end and then we can ask questions?
No, please interrupt me.
Good morning, everyone. Welcome to the first talk of this morning, which is on sharp anti-concentration via Choquet theory and related ideas by Moksha Madhiman from the University of Delaware. And Moksha, please.
Thank you, Gautam, and thank you to the organizers for putting together this conference. I'm sorry I'm not able to be there in person, but you know, I'm glad to participate anyway. So thank you. So what I'm going to talk about today is I'm going to give a bit of an overview. It's a bit of a survey, and most of this work was done a few years ago. But I think it would be of interest to many of you, and I'm not sure it's that familiar. So I thought it might be a good opportunity to present this material. This is joint work with James Melbourne, who is now in CIMAT in Guanajuato, Mexico, and Peng Shu, who's now at Eastern Michigan University. And right, so let me get into it. So the basic quantities of interest that I want to talk about, is this large enough to be seen?
Maybe a little more larger.
Sorry?
Yeah.
Is this large enough?
Maybe just a little larger?
Yes, a little larger.
Okay, yeah, sure. Okay. All right. So the thing that we want to study right now is we're going to look at some let x be a random variable. Okay, I'm going to consider both discrete and continuous random variables. So if x is discrete, and let's say it has some probability mass function p is discrete, and what I mean by that is that it takes values, or it takes values in a countable set. So values in some countable set A takes values in a countable set A, then we'll write M of X for the maximal atom. Right, and this is the probability mass function. So what I mean by this is just I'm looking at the maximal probability that X takes the value, X takes a particular value, right? And on the other hand, if X is has a density, so for example, I mean the prototypical example is, let's say X takes values in some Euclidean space, has a density f, then M of X will be the infinity norm of f, which is just the essential supremum, right? And in the case where, so of course, if this is just the maximum of f of x, if let's say f is bounded and continuous. So this is our quantity of interest. It's just either the maximum of the probability mass function or the maximum of the probability density function. And why is this quantity of interest? Well, I mean, it should be evident that this is a basic measure of spread of the random variable x. But let's make that more explicit with some remarks. So first of all, if we have small m of x, whether it's discrete or continuous, small m of x means that the random variable is spread out, right? Because the largest atom or the maximum of the density is small, means that it has to be spread out in order for the total probability mass to be 1. So small m of x means x is spread out. So this is somehow capturing the spread of a random variable. So what is, I mean, also this is related. This is related to the notion to a Renyi entropy. So connection to what is called, I mean, this is just a matter of terminology, but let me say it anyway. Connection to the Renyi entropy of order infinity, which is just, or sometimes this is called the min entropy or the min entropy, which is just, I mean, the way that this is usually written is h infinity of x, and what this refers to is minus log m of x. Okay, so this quantity is sometimes called the min entropy, and it's always a lower bound on the usual entropy, right? So it's a fact which I'm not going to bother proving, but if you've come across the notion of Shannon entropy, which is usually just written an h without the infinity. So if you look at Shannon entropy, which can be defined again in both the discrete and continuous settings, in the discrete setting, it's just minus the sum of p of x log p of x. In the continuous setting, the sum is replaced by an integral. So this is always a lower bound. The infinity Renyi entropy is always a lower bound for the Shannon entropy. But we are not going to care about the Shannon entropy in the stock. We are just interested in the infinity Renyi entropy, or in other words, the maximum of the probability mass function or the probability density function in its own right. So one thing, right. So I mean, and one thing you will notice is that if you think about the fact that small m of x means that x is spread out. So if you want to think of a measure of spread, then h infinity is better, is really a measure of spread, because you know the smaller m is, the larger h infinity is, whereas m of x itself is really an inverse measure of spread. So let's keep that in mind. And I'll also mention that there's this so more generally, we won't consider it today, but actually one can build on what I'm talking about today to more generally consider what is called the concentration function. So one can consider the concentration function, and what is meant by the concentration function is this function here for a fixed epsilon, for fixed epsilon, which could be greater than or equal to 0, you could consider the supremum over all x, the probability that x lies in a ball of radius epsilon around x. And notice that, for example, in the discrete setting, if you take epsilon equal to 0, this is just the maximal atom, right? Whereas in the continuous setting, I mean, when you take epsilon going to 0, this should be, if things are regular and nice, then in some limit, if you divide by the volume of the ball, for instance, you should get the maximal density. Okay, so anyway, so more generally, one can consider this concentration function, which is, I mean, sometimes these things, this is called the small ball probability. This is the probability of lying in a small ball, and there's an extensive study over the decades of estimates for the small ball probabilities, which find applications in many areas. So many applications to, for example, to Gaussian processes, to Bayesian nonparametrics, and so on, apart from being in interest in their own right. So anyway, but I mean, all this is to say this, the study of this object is well motivated, this M of X. And so what can we say about it? And, what do we want to, so what's our setting now? So so maybe in order to, maybe I'll mention some known results about M of X and how it behaves under various operations. So known results. So the first known result I want to mention is sometimes called so this is due to Littlewood and Offord. In 1943, and it was improved by Erdős in 1945. And what they showed was, this is in a discrete situation. So if we consider x1 to xn being IID Bernoulli half random variables, right? So they just take values either +1 and -1 or 0 and 1 with probability half each. And if you fix, so for a fixed vector a1 to an, with each of these AIs non-zero, okay, for every I, we can set SA to be this linear combination, the sum of AI xi, right? And then we can ask for the maximal atom of SA. When is that maximized? So Erdős proved that this is maximized when you take A star to be, so where A star is just all ones, right? For instance, so which is basically the binomial distribution, right? If the AIs are all one, you end up with a binomial distribution. This gives you the largest maximal atom, right? And this, it can be shown, this maximal atom behaves like order 1 over square root of n. And this fact is extremely useful. It has many applications, for example, in random matrices and so on. This is, but at the heart of it, what this is doing is saying that this, it's a statement about, when this maximal atom of this linear combination of Bernoulli random variables is maximized, right? For what values AI is this maximized? So there's a classical result, and there are many more. This has been investigated to great depth by many people, I'll mention, for example, there's a nice survey by Hoy, Nguyen, and Van Wu on small ball probability, which looks at many extensions of this. There's lots of work in additive combinatorics and so on, which explores these things, in more general settings. Okay, so that's one known result. Here is another.
It is scale invariant.
Which goes.
Moksha, if
Sorry?
you multiply all the AIs, that doesn't change the maximal atom. No?
That's right. That's right. Yeah. So I could equally well have picked A star equals 2, 2, 2, 2, 2. It doesn't matter, right? But what the point is that if I pick all the AIs to be equal, that gives me that gives me an extremal situation, right? That's basically like the binomial distribution, even though it may not be supported on 0 to n. In general, it may be supported on something else, but it's essentially some scaled binomial distribution, which is extremal. Okay, thanks. So now another known result. This one is due to Rogozin in 1987. Says the following thing: if x1 to xn are real valued random variables. And you want to maximize, let's not bother with, because I'm not putting some constraint on the distribution like Bernoulli or something. I don't have to bother putting some scalar parameter here. I'm just going to look at the sum of the xi, and I'm going to ask if I can get meaningful upper bounds on this quantity, right? And one meaningful upper bound that one can give is the one that Rogozin came up with, and he pointed out that that this is always bounded by the maximal atom of the sum of uniforms. So where these UIs are independent random variables, uniform on an interval. Of course, which interval doesn't matter, only the length of the interval matters, because I mean, the maximal, in this case, it's not the maximal atom. In this case, it's the maximum of the density. The maximum of the density is not going to care about translations of your underlying random variables. So uniform on an interval such that m of ui is equal to m of xi, right? So in other words, because the maximal density of a uniform is just the density of the uniform at any point in its support, which is going to be 1 over the length of the interval, right? So this is going to be 1 over the length of the interval. So that determines the length of the interval, basically, right? So the length of the interval is going to be 1 over m of xi, essentially. And so this gives one way of bounding the maximum of a sum of independent random variables. So these are, I should have said independent, right? Are independent real valued random variables. Then this is true. Okay. And it was observed by Juskevicius much later. For some reason, this was not noticed earlier, but Juskevicius and Lee in 2015 observed that this also holds for random vectors, that this holds for xi in RD instead of just real value. Okay, so so that's nice. We have these bounds on the maximal atom or the maximal density, but you can also ask for another type of bound. So this bound, you're replacing these xi's by uniforms, but it doesn't tell you how to bound the maximum of the sum if, for example, the maximal density of each of the xi's, right? I mean, that's it does tell you that, but it's sort of implicit in some sense. So you can ask for a more explicit description, and that was given by Bobkov and Chistiakov. So Bobkov and Chistiakov in 2014 showed that if x1 to xn are independent RD valued random variables, then if you look at m to the minus 2 over d, it turns out that this is the right functional to consider of the sum of these xi's, I going from 1 to n. This is greater than or equal to 1 over e times the sum I going from 1 to n of m to the minus 2 over d of xi.
Moksha.
Okay, so this is more explicit. Right. Yeah, question?
Yes. So in the 2015 result, the uniform is on the ball or the boxes?
Right. Okay. Very good point. So the uniform is on Euclidean balls. Okay. So so here I should say where UIs are now uniforms on Euclidean balls. Okay. So I'm going to I'm mentioning all these results, but I'm going to describe some results that we obtained that basically unify and generalize all of these, right? So in which the role of Euclidean balls will become clear. So anyway, so Bobkov and Chestakov proved this more explicit result, where, I mean, essentially this is a corollary of the Rogozin result combined with some other things. So, Rogozin is telling you that if you want an upper bound on the maximal density of the sum, you can restrict yourself to uniforms on intervals or on Euclidean balls more generally. Whereas Bobkov Chestakov said, okay, now you're looking at the maximal density of a convolution of uniforms on Euclidean balls. Can you bound that in some quantitative way? And it turns out you can, and this is the quantitative bound. And here, so the thing to note here is that this constant 1 over E, the constant 1 over E is the best possible if we want a constant that is independent of the other parameters. That is independent of both n and dimension. That is independent of the number of summands and the dimension. If you want a constant if your constant is allowed to depend on n or d, you can potentially improve this. But this is the best constant if you want a universal constant. So in particular, you cannot get one. So I mean, if one can think about this. I mean, both these results, the Rogozin result as well as the Bobkov-Chistyakov result, these are in some sense analogs for maxima of the density of well-known results in convex geometry and probability. I mean, in convex geometry, one has the Brun-Minkowski inequality, which is doing something similar. It's saying that when the Brun-Minkowski inequality is really about the Renyi entropy of order 0, if you like. It's about the support, the volume of the support of your random variables. Whereas in information theory and probability, there's a well-known entropy power inequality due to Shannon and Stam, which says that Shannon entropy, also satisfies. There is an analogous inequality there. I mean, all of these things are saying if you know something about the spread of individual random variables xi, and now you add them up, what can you say about how can you minimize the spread of the sum, right? So that's what all of these that's what I mean. This is analogous to the Brun-Minkowski inequality or the entropy power inequality. It's just that you're using a different notion of spread here, which is the maximal density instead of, say, the Shannon entropy or the volume of the support, right? Which is which in the so in the convex geometry case, you don't usually speak about it in terms of random variables. You just talk about it in terms of volumes of set, but you could speak about it in terms of random variables as well by thinking about uniforms on some random variables, for instance, that are supported on some sets. Anyway, so so these are known results, and I'll mention one more known result before talking about how we can generalize them. So the fourth known result is due to Lifshitz, Fauris, and Pivovarov. This is in 2016, and this is building on Rudelson and Vershinin in 2014. And what they showed is that suppose x1 to xn are independent, of course, independent real valued I'm sorry, random variables with the maximal density of each xi being less than or equal to L, for example, let's say L for every I. Then if P is a projection, so P from Rn to Rk is a projection to a k-dimensional subspace. I mean, I can identify the subspace with Rk, so then M of Px is less than or equal to Cl to the power k, where the C is an absolute constant. So, so this was proved by Rudolfson and Vershinin that you have such a result, and what so note Rudolfson and Vershinin 2014 showed this for some C, and Lifshitz, Pawaris, and Pivovarov optimized the constant C. And it's an ugly constant, so I'm not going to bother writing it down. But in particular, if, for example, this is related to this Bobkov-Chistyakov result, because if you take k equals 1, you look at projections to a one-dimensional subspace, that is essentially you're looking at convolution, right? You're looking at the sum, possibly a weighted sum. But anyway, what this is saying is that if this is saying that this is less than or equal to C to the k, but k is 1 here, so this is just C. If M of xi is less than or equal to 1 for every I, right? So that is what this would boil down to in that case. If k is 1 and L is 1, this would boil down to this result, that if all these maximal densities are bounded by 1, then the maximal density of the convolution is bounded by C. Right. So so we have all these results, and now we are in position. So before I move on, any questions about these known results? Okay, so let me tell you about what we did. Sorry?
E is independent of them.
What's the question?
Is C independent? This C is independent of them. Right? The number
Yes, C is independent of everything. C is an absolute constant. It doesn't depend on anything here. Yeah. So, right. So anyway, so our contribution is to develop whoops. A general mechanism for proving such results, building on what Rogozin and Bobkov and Chistyakov did, which in particular, which unifies all of the above and also improves them in various ways. So for example, what's one unification? I'll mention one result in the continuous setting. So in the continuous setting, one theorem. So this is with Melbourne and Shu. So let x1 to xn be independent RD valued random vectors. And P be a K by N projection matrix. Then there exists gamma I in 0, 1, depending only on P, such that the sum of these gamma i's is equal to K. And if you look at the maximal density of, you look at this thing, P tensor the identity applied to X. I'm going to explain this in a minute. This is less than or equal to C of dk times the product going from 1 to n, m to the gamma I of xi. So what do I mean by this? Where again, this constant C of dk is ugly. This is an explicit constant depending only on d and k. So what do I mean by this? I'm thinking, so each of these xi's are RD valued random variables. Oops. Okay, so apparently I might need to shut off my video because I need to plug my laptop in. I'm sorry. Can everyone still see the screen and hear me?
Yes.
Yes.
Okay, so right, so so what do I mean by x here? So this x, I need to think of this as a vector in Rd to the n, right? I'm concatenating all these these n vectors in Rd, and just to be clear, what is the tensor product doing here? So for example, just to be clear, for those who don't manipulate tensor products on a daily basis, suppose for example this P was a projection from R3 to R2. So let's say it was something like this, and my x is now going to be x1, x2, x3, right? Each of these being in Rd, so this is an Rd cubed, right? And so P tensor ID, in this case D is so P tensor ID of x would basically be the vector which is given by a11 x1 plus a12 x2 plus a13 x3. So it basically treats each of these vectors as if they were just scalar random variables, right? So and this thing lies in Rd squared, right? So this is what this tensor product is doing. So in particular, in the case where this projection, in the case where k equals 1, for instance, you would just get a convolution, right? So one thing that this immediately gives, so note that an immediate consequence of this is if all these m of xi's are bounded by 1, for instance, or by L for that matter. Anyway, let's take 1 for simplicity. If all these m of xi's are bounded by 1, this says that the maximal density of this projection is bounded by the C of dk, right? So so this is the point. So this generalizes the Lifshitz-Paurus Pivovarov result that we just talked about here to the case where instead of each of the xi's being random variables, they are now random vectors, right? And so the constant C of dk that we find are sharp in some sense. So for example, I mean, one consequence of this is that we get so consequences. So first consequence is we recover the Lifshitz-Paurus Pivovarov 2016 result when our dimension is 1. Second consequence is we recover, in fact, we not only recover, but we improve on the Bobkov-Chistyakov 2015 results, which, remember, what they showed is they showed that m to the minus 2 over d of the sum of xi for random vectors is greater than or equal to 1 over e times the sum of m to the minus 2 over d of xi. And what we get is, instead of this 1 over e, we get, I mean, our constant would now be c of d1, because in general, our constant was c of dk, but now we are looking at projections to a one-dimensional subspace, basically. So that's c of d1. And that constant turns out to be gamma, written in terms of the gamma function. This turns out to be this thing here, which it turns out decreases as d goes to infinity to 1 over e. So basically, it turns out that this here is the Sharp constant that depends only on d. That depends only on d, whereas what Bobkov and Chistyakov found was the Sharp constant independent of d, right? So we get a dimensional Sharp constant, if you like. Anyway, so we can basically recover all these previous results, except I haven't told you how to recover the discrete result, like the Littlewood offered Erdős stuff. But maybe I'll say a bit more about that later. So what are the proof ideas here?
Recovering the Bobkov-Chistyakov, is it straightforward, or I'm not sure this one.
Yeah, I mean, it's straightforward in the sense that literally by, it's just plugging in. Yeah, you just plug in k equals 1 here to recover the Bobkov-Chistyakov result. In fact, to improve it, right? If you plug in k equals 1 here, you get on the left-hand side just the sum of the xi's.
Okay.
Right. I mean, take your projection matrix to be the, to be the to be just the row vector 1 1 1 1 1.
Okay.
Right. Then essentially this p tensor ID of x is basically just the sum of the xi's. So in that case, you get exactly the Bobkov-Chistyakov setup, but your constant on the right hand side is now c of d comma 1. Right, and c of d comma 1 improves the Bobkov-Chistyakov constant of 1 over e, because it's the best constant that depends on dimension now. Does that make sense?
But the sum of this m of xi is missing. Is it some normalization or something?
Okay, so yes, so okay, so yeah, so that takes, I mean, all right, I mean, that's you can easily, so you can scale each of your xi's so that your maximal density is 1, and then you just play around with that and you get this. Okay.
Okay.
So there's some homogeneity here, right? So you can scale each of your xi's so that the maximal density is 1, and then apply this result.
Okay. Okay.
Yeah. Okay. So all right. So what are the proof ideas? So it turns out that one of the proof, the key proof idea actually goes back to Rogozin, who recognized the role of, but somehow, Rogozin sort of recognized the main idea, but maybe didn't implement it in the most efficient way. So our basic observation was that we can implement it more efficiently. And what is that idea? That idea is that, what are we trying to do? We are trying to maximize, for example, just the simplest setup. Let's not worry about projections. Let's just look at convolutions. So we are trying to maximize, this maximal atom or maximal density of the sum of the xi's, subject to knowing m of xi for each I. Right. So that's what we are trying to do. So let's just note that this this maximum, what is it? It's, after all, this is just the infinity norm. So this is just the infinity norm of the convolution, right? If f1 to fn are the densities of x1 to xn, then this is the infinity norm of the convolution of f1 to fn, and this is a convex. So the infinity norm is a convex functional because it's a norm. So this is a convex function composed with a multilinear, composed with something that's multilinear, okay, because convolution behaves nicely. So the point is we are trying to maximize something that's like convex composed with multilinear. So you might expect, I mean, when you're trying to maximize a convex function over a convex set, over a compact convex set, which we are dealing with because we are subject to, we know what the maximal density of each of the xi's is, which means that each of those, the distributions of each of the xi's, these densities fi are constrained to lie in some compact convex set. That's essentially what this is saying. Okay, it may not be compact, you have to, but okay, let's one can approximate by things with compact support and so on. Let's not worry about all that. But anyway, the point is that this looks like maximizing a convex function over a compact convex set, which we know happens at the extreme points, right? That's the Krein-Milman theorem. So by the Krein-Milman theorem, essentially the idea is that by the Krein-Milman theorem, it suffices to look at extreme points. But extreme points where it suffices to look at extreme points. But what is our constraint set here? Extreme points of the feasible set, right? But what is the feasible set? The feasible set is these constraints, the constraints on the distributions of the xi's, right? We know the maximal density of each xi. So those are the constraints. So that means what we are looking at is things like this. We are looking at, let's say, Pm, which is, let's say, all densities on Rd with maximal density with basically infinity norm, with infinity norm equal to m. Okay, or less than or equal to m, it doesn't matter. So infinity norm less than or equal to m, right? So the point is that this we can look at the extreme points of this thing. That's what is going to be relevant here. So one of our main observations is that we can characterize the class of extreme points here, in fact, in much more general settings. So here is a general theorem. So let let EI be Polish spaces with Borel probability measure, let's say alpha I, and so if phi mapping the product of these P MIs of EIs. So these are this class of probability measures on the EIs which have maximal densities with respect to alpha I. These alpha I's. So these are not Borel probability measures. Sorry, just Borel reference measures. Reference measures alpha I, which would be Lebesgue in the case of Euclidean space. And so now if you have some function here going to R, which in our case is the infinity norm of the convolution, right? Which is is coordinate convex in each coordinate and lower semi-continuous, then the supremum over basically all mu1 to mu_n in this product space of this phi, the supremum is achieved. It suffices to consider the supremum over mu1 to mu_n in the product of the extreme points, basically. So the products of the set of extreme points. And what is the set of extreme points? So where this P mi star, or let me just Pm star of E is the collection of probability measures mu with densities of form d mu by d alpha of y is equal to m So basically, I mean, the interesting, there are basically two situations that arise. So example, the interesting situation is if alpha is non-atomic. So if your reference measure is non-atomic, then this second term drops out, no second term. So in this case, the extreme points are of the form d mu by d alpha is m1u of y. So these are basically uniforms, right? So these are uniform measures on some set. So these are uniforms on some set. Are uniforms on some set, right? Whereas, I mean, there's these singleton, atoms that appear on the side. These appear in the case where your reference measure has atoms. For example, in discrete situations like the Littlewood offered the situation. And anyway, the point is that one consequence of this is this very general. So as a corollary, one can observe this general fact if G is a Polish locally compact group with a non-atomic R measure, and x1 to xn are independent G-valued random variables with densities f1 to fn, then once again using m for the maximal density, so m of x1 to xn. Now I'm using product instead of sum because I'm denoting my group may not be abelian. So I'm using product notation instead of sum notation for my group. But basically, I mean, in the case where G is just Euclidean space with my group operation being addition, this reduces to what we were looking at before. This is less than or equal to the supremum of m of u1 to un, where the supremum is taken over all independent G-valued random variables, u1 to un, with ui uniformly distributed. Whoops. Maybe I should just write it like this. With ui uniform on some subset of G. So uniform on AI with AI being a subset of G, and satisfying that M of UI is equal to M of Xi. Okay, so this is basically everything that we were doing before, except that you have to take the supremum over all possible sets. You don't have it's not obvious that you can, there's no notion of a Euclidean ball in a general locally compact group. You have to allow yourself arbitrary sets, which can have weird shapes, right? But what you're guaranteed is that it has to be a uniform in the sense that your density with respect to the Haar measure has to be constant for these random variables UI. And then to go from this result that says, you can limit yourself to uniform random variables on subsets of your group to the extremality of Euclidean balls needs an extra step, and that extra step comes from the notion of rearrangement. So note is that in the case of G equals RD, to go from arbitrary uniforms to uniforms on Euclidean balls, one uses rearrangement inequalities. So in RD, you have this very nice fact that spherically symmetric decreasing rearrangements behave very nicely. And one implication of the Braskamp-Lie-Blutinger rearrangement inequalities is that if you are trying to maximize such a maximal density of convolution of uniforms, then actually this is achieved by taking Euclidean balls. So rearrangement inequalities. So this is due to, for example, Rogers, Braskamp, Lieb, and Blutinger. So anyway, basically by combining this Krein-Milman theorem observation and this identification of extreme points with rearrangement inequalities, one can recover all of these results and unify them, right? Not just the continuous results, but even the discrete results. Because this covers the case where your Haar measure can be atomic. And so basically this, for example, this gives you results on the integers, like the Littlewood offered or business. There are various additional things to take care of there, which I don't have time to go into. But anyway, I mean, the point is this, this way of thinking about things as, basically using a Krein-Milman theorem to get it down to uniforms or almost uniforms. These things, if you have atomic Haar measures, then this is basically, this thing here is almost uniform. This part is uniform plus like one atom that may, that makes it almost uniform. And that appears because of the fact that for a given value of maximal atom, there may not be a uniform with that maximal atom, right? Because if you're in a discrete situation, for you to have a uniform distribution, your maximal atom is just any atom, and that would have to be 1 over an integer, right? The probability would have to be 1 over an integer, and your your prescribed value of M may not be 1 over an integer. So this is why you have this almost uniform thing that arises in the discrete setting. But anyway, so the point is that this is a nice unification of the story. So for details, I would there's this paper on the archive with Melbourne and Shu. So the original paper is 2017, and this was actually never published, but we are preparing an updated version of this, which hopefully will appear on archive at some point. But anyway, there was one other thing I wanted to mention to to connect to more classical convex geometry topics, which is a connection of these maxima of projections to Boozman's theorem in convex geometry. But I think I might be running out of time, so let me close here. And if there are questions about the connection, I'm happy to answer offline or whenever. All right. Thank you very much.
Thank you, Moksha, for the very nice talk. Are there any questions?
Just few minutes. He
maybe
has asked the question. We can. You can maybe say us a little about the Boozman problem. Sorry.
Like 5 minutes.
Sure. Okay. I'll give it a shot. So Boozman's theorem is the following fact. Boozman's theorem, and this goes back to 1949. So this, I mean, the easiest way to say this is using the notion of an intersection body. So let me define that first. So for any compact set, K subset of Rd with 0 in its interior, we can hold on one sec. Okay, I'm sorry, I'll have to plug my laptop in because it's going to die literally any second. Okay, so for any compact set like this, define R, which is a function on the sphere, by R of theta being the volume, the d minus 1 dimensional volume of K intersect theta perp. Right. So basically, I'm looking at the hyperplane passing through the origin that is perpendicular to theta, and I look at the so I can think of really I'm thinking of K being a compact convex set, and 0 is in the interior. In fact, we'll look at symmetric convex bodies in a minute. And so then we have this direction theta, and I have this basically this hyperplane that's perpendicular to theta. So this is my theta perp, and then what I'm looking at is this cross-sectional volume, right? So this is K intersect theta perp is this cross-sectional volume. I don't know, I'm not drawing the convex set very nicely, but this has some width like that. So anyway, so we have this cross-sectional volume, and I'm measuring the cross-sectional volume here. So that's my R of theta, right? And then you can define, so the star-shaped body whose boundary by the points theta R of theta. So basically, in direction theta, I go out a distance R of theta. From this body, this is my K, I create a new body where if I look at direction theta, the distance I go out is R of theta, which came from the d minus 1 dimensional volume of
Moksha, we cannot
the cross section of K.
We cannot
right?
see.
And in this way, I get some star-shaped body, right? These contain all the rays because I'm going out a certain distance in each direction. So I get the star-shaped body. This body is called the intersection body of K.
Moksha, I think your notebook has frozen, so we can't see
Oh.
anything that you're writing.
What happened? I'm not sure what happened.
Okay.
Okay.
But if you would just like to say in words, that
Yeah,
would also
sure.
be
Yeah, yeah.
fine.
Sorry?
You would just like to say this in words, I think that would be also good for us.
Oh,
Did he get logged out?
no, he's still there on other device.
The battery went
Okay, maybe start it again. So hold on. Hello?
Yes, we can hear you.
Can you hear me?
Yes, yes, we can hear you.
Okay. So, okay, are you able to see the image now?
No,
No. I think, yeah, maybe.
we just see that you have started screen sharing. This is the message that we see on the screen.
Okay.
Just the internet.
Yeah. On device, if power is low, sometimes it may not go well. It's, yeah, I
I will
think-
choose to say it.
Yeah, well, anyway, there's this.
voice is-
Sorry, are you able to see it?
No, we are not able to see you or the screen, and your voice is also a little bit, like what's the word like?
choppy.
Choppy. Yeah. But I think it's like you would like to say it in words or
Okay.
like,
I'm sorry about. Yeah, I'm sorry about these logistical issues. The point is that are you able to hear me at least now?
yes.
Yes.
Okay. So yeah, let me try bring the share. I think it's yeah. So okay. So the point is that one can define this intersection body of a symmetric convex body as this, as a star shape with, where the distance you go out in a direct theta of the of the body K intersected with theta per. And then Boozman's theorem basically says that this intersection body, if you start out with a symmetric convex body, then the intersection body is convex, right? And that's really a statement about the niceness or the, some kind of convexity about these cross-sectional volumes as you change theta, as you rotate, as you change theta over the sphere, you get these cross-sectional volumes and they're all related in some way. And that's what Boozman's theorem is capturing. And it was first observed by Keith Ball that Boozman's theorems can equivalently, I mean, he didn't state it in this language maybe as explicitly, but it was essentially recognized by him that Boozman's theorem can be stated as an observation about the maximal density of a projection of a random vector that is uniform on your convex body. And so the point is that this that basically this maximal density of the projection, 1 over that maximal density turns out to define a norm. And that norm is sometimes called the Keith-Ball norm. The related convex bodies are called Keith-Ball bodies. Anyway, so I was hoping to show you that Boozman theorem is essentially equivalent to the statement about this maxima of projections, and in fact, as proved by Keith Ball in the case of log concave random vectors, and then later one can use related results of Sergei Bobkov and so on to show that for this general class of so-called convex measures, if you have a symmetric convex measure, you can define an intersection body corresponding to that, and that turns out to be convex as well. So these kinds of results, I mean, these are sort of in a reverse direction, because these give you, instead of upper bounds for the maximal density of projections, these are related to lower bounds for the maximal density of projections under some convexity condition. And these are related to what are called reverse entropy power inequalities. And this material is surveyed in another paper that we wrote with James Mahon and Peng Shu. And that survey is called Forward and Reverse Entropy Power Inequalities in Convex Geometry. So that might be of interest as well. So that's all I wanted to say.
Thank you, Moksha. Let us thank the speaker. Meet again at.
Thank you.
We meet again at 10:45 for the next one.
Are we doing the photograph now?
First, afternoon. First, yeah.
Oh, great. Okay.
We have. So what we tell him is about.
It's okay. I have the book if you want to discuss the.
If you wanted the title or something.
Check this one.
Oh,
It's also on the website.
take it back from you. One of you can put it, and whoever did, you add it to this. The other person will. So the what you can do is you can go back to split up by that. क्या हो रहा है इसमें तो रजिस्ट्रेशन भी जनरली बात नहीं करता है चॉपीनेस के बारे में चॉपीनेस के बारे में दोनों का probably
If there are some spots.
I think control.
And it just small number. Yes. Yeah.
Yes. Last number. Let's just say it's a mini course like this on everyday life. Yeah. Take a shot.